things faster. I'm Gleb Peregud from Silversoft from Warsaw. I'm working on a few different projects. Most of them are interesting for startups all over the world. Today I would like to tell you about the Oortle, almost linearly scalable publish subscribe system. Okay, what is Oortle? Oortle is the project for publish subscribe, which is supposed to handle hundreds of thousands of concurrent connections from browsers. The idea behind it, I mean, the product which was for which Oortle was created is a live blogging system called LivePress. It is nearly complete. Product which we are building is a live blogging system. It's tasked to provide real-life updates to all the clients, all the visitors of certain blogs. So whenever author of the blog updates a blog post, this update should go to all the clients, all the visitors of the blog instantly. So, and the product is aimed for very big events, for example, like live blogging information about the, let's say, Steve Jobs presentations when he launches new products. Then a lot of people are tuning in and listening and trying to be on time what he says, but not everyone wants to see the video because it is too time consuming. So there are few places where some journalists just keep updating blog posts on their sites about everything the, for example, Steve Jobs says. So basically, the main requirement of this publish subscribe system is to be able to send out updates to clients, hundreds of thousands of them, in less than 1.5 seconds end-to-end latency to all of them. So it makes things a bit hard because we have to optimize all the things. But let me. No, so I would basically this talk is about. Oh, it's too small. The talk is about presenting just a use case. I want to talk about the problems which we encountered while developing a very large system which is supposed to handle hundreds of thousands of connections of clients. So I will share the problems we had. I will share some of the solutions we employed. I will ask some questions because there are some problems which we have not yet solved. And I hope you will just get a grasp about the, you'll get a feeling how to approach bigger projects than you're usually dealing with. So the topics which I'm going to cover is API, discoverability, which is very important in the cloud settings, performance, scalability, and reliability. So the system itself, basically it consists of 4 parts. It's the blog engine itself, which displays things to the user. There is a LivePress web service which is running somewhere on the internet, and blog is communicating with the LivePress web service and handles authentication, all the boring stuff. And when something changes on the blog, LivePress passes this information to the Oortle cloud, which handles all the connections between Oortle and all the web browser, the clients, the visitors of the blog. And yeah, clients browsers. So that's the system in general. But we're most interested in the Oortle part. So basically, we have 2 basic nodes, which is control node and worker nodes. Control node is used for controlling the cluster. Obviously, the worker nodes are handling the connections itself. So usually there is one control node and multiple, probably hundreds of worker nodes. And also to be able to retain good fault tolerance and reliability, we have to provide some failover for control nodes, because it's a single point of failure, which we always have to avoid in any reliable systems. So whenever, okay, I'll talk about it later. And in case there is a situation when we have not anticipated so much attention to our system, our event, and we have not 1 million users watching, but 2 million, we are in such situations we start more worker nodes when we have to, just to have some margin of error to be able to handle some things which we have not thought about. So let's get back to the API. So API, since we're dealing with the web browsers, we have to be able to communicate efficiently. The problem with browsers, some of them are pretty bad, like Internet Explorer 6. So we have to be able to handle all of them using different transports. We implement WebSockets, Flash transport, XML HTTP request with cross-origin request something, a script tag long polling connections, and webhooks for some auxiliary stuff which is not really important. What is the problem here, which we had to solve? The browsers itself. The problem is that only very modern browsers support WebSockets. So just at the moment, it's probably 5 to 7% of users can make use of WebSockets. And we want to use WebSockets because they're the most efficient here and they're native. Fortunately, almost all of the browsers have Flash support. So if there is no WebSockets, we try to use Flash. If there is no Flash, we try to use HTTP request, which is present only in new browsers. I mean, we are always dealing with cross-domain requests. There are no single-domain requests, so normal XML HTTP request doesn't work. We have to use the one with support of CORS, which is pretty recent, and for even older browsers like Internet Explorer 6, we have to use just script tag long calling, which works cross-domain, but it is hard to implement because there is no reliable way to, no easy way to reliably detect errors using this transport, but there is some solution. So when we implemented the WebSockets, we started with our own implementation one, but when more versions of WebSockets appeared, we decided to make use of Mistletoe. The problem is it got discontinued, so we can't use it anymore because or we have to switch to something else, or we have to maintain it ourselves. But we never really used all of it, so we really needed only a small part of it, which handles parsing of WebSocket protocol. And because the Mistletoe itself uses a lot of processes for each request. So if we would use it directly, then we would double or triple number of processes on our nodes. But when we have, let's say, 1 million or 2 million of processes on node, with double or triple it, and so it is a problem. Especially that the memory was usually a problem due to TCP/IP connections, which are taking a lot of memory in Erlang. We'll talk about it later. So we went up in extracting protocol WebSockets stuff to different projects, so we can maintain only the interesting part. Maybe someone else will use it for other projects. For XML HTTP requests and script tag connections, we extracted such a thing as script caller, which handles cross-domain requests between from one domain to service in other domains reliably on, I think, any browser which is out there currently. It solves the problems with the error detection of the script tag transport which there are like 5 ways to detect errors if we use it. So it's a bit hard, so you can use it if you want. Okay, there is way too less space here. This is the topic of discoverability, because if we are running a system which should handle a lot of requests, we probably would like to use some sort of cloud. So we chose obviously amazing EC2, and if we have amazing EC2, we have to be able to discover nodes which are started there, both by our own tools, which is easy because we started those nodes ourselves, so we know where they are. But clients should be able to connect to those nodes. So our solution, which is not visible here, is to use S3 to store server lists of the current cluster, Oortle cluster, so clients can connect to it. We used service Zerigo for dynamic DNS, which helped with some of the problems. And for internal stuff, we used amazing EC2 tags for automatic instance management, which is another topic which I will cover later. Yeah, performance. If we have such large system which is supposed to handle a lot of clients, we have to optimize stuff. There are probably 4 problems which we struggled the most. The first one is latency, and since we have very tight requirements here, we optimize it a lot. Fortunately, it was done previously, and by the way, if you're following Erlang mailing list, you should have seen the contest run by Joel Raymond for optimizing broadcast speed. It was called Janus or Hot Wheels. It was $1,000 prize for solving a specific problem. And Oortle is evolution, next step of evolution of Janus, basically. So it's the same project. And you can find the open source version of old Janus out there, which is even now pretty useful. So the problem with latency was there was no good way to broadcast stuff fast enough to be sure it will be handled. It will be handled fast enough, especially since we used EC2 initially. Problem with EC2 is that the latency, network latency there, varies a lot during the day. Sometimes it happens that in the morning it works perfectly and we're able to maintain our good latency, but in the afternoon it basically sucks. There was no good way to ensure that the latency requirements were solved, because it was not our infrastructure which was slow. It was amazing infrastructure which was overloaded for some reasons. And we basically ended up by using a combined solution. Our main server is hosted in some location center with a good connection, guaranteed bandwidth, and very good hardware. And in case if we are unable to solve, to handle, let's say, currently that that hardware is able to handle about 750,000 connections simultaneous with broadcast latency, end-to-end broadcast latency less than 1.5 seconds. So this is our goal. So if you would need to handle more connections, we just start more EC2 nodes. They might be not as fast as normal physical hardware, but this way we are able to scale up and down depending on our current needs. So if you need latency, EC2 sucks. Don't use it, because you don't have full control over it. So in some cases it will fail you. The other problem which was to be solved is socket accept rate. The problem is that in the modern accepting TCP connections is a thing which is handled by the kernel, and there is a lock on one socket always. So there is a queue of threads waiting for the accepting connection, but there is a lock. So there is no really good way to use more than one core to accept connections on a single socket. So assume we have a Steve Jobs event, or someone else, and we have a surge of 1 million connections. And the problem is usually, if we have 16 cores per hardware, we will not be able to use all of them, because only one core will be able to accepting those connections. So this is we cannot avoid it because it's handled by the kernel. So there are a few solutions to this. Just add more servers, add more sockets, listen on multiple ports, or add more acceptors per one socket. It will speed up things, but it will not avoid circumvent the limitation of a lock on a single socket. That's the thing which I've mentioned. So the contest, which was claimed by Cliff Moon about broadcast speed in Erlang running on EC2, it was solved by changing the priority of the broadcasting process, Erlang process, inside the virtual machine to send messages to processes which are handling particular connections. It was a good solution up to the point when we find out that it screwed up socket accept time. It became very unstable, and whenever there was broadcasting, almost everything other, which is mainly accepting sockets, stopped. So we were not able to gradually proceed with accepting sockets. It was hanging and causing timeouts and stuff. Why those socket accept types are so important? When we are using script tag transports, we have to start one connection per interaction between client and server, because that's how the script tag works, and XML HTTP requests too. We could use some infinite iframe solutions, but we found them to be too complex to be stable enough. We might implement it in the future, but we'll see. There are other things which are important. If you have a really big system, we're not really able to take a look at particular problems. We will always, if we have million connections, we'll always have timeouts, broken connections and stuff. There will be always some noise of errors in our system. So there is no point in looking at one particular event, because there are always some events there, and we cannot avoid them because they are out of our control. So the point is, we have to instead of looking at specific problems, specific errors and crashes, we have to monitor the error rates in our whole cluster. And if we see that error rate is increasing or is above some level, we know there is some problem in our system. So basically, such things as real-time statistics are really important in such systems. So, but on the other hand, they can be costly, because to gather statistics from, like, let's say 100 nodes, there is a lot of communication between those nodes to gather it and aggregate. So such things, they are important but not essential. So if in such systems you have to design such elements in a way that they can be turned off or limited, or they should be self-limiting to avoid disturbing the main goal of the system. So for example, real-time statistics, which are really good for writing and stuff and monitoring, but they can be costly, so they have to be designed in an appropriate way. Scalability. That's the other thing which we struggled with. And we found out that scalability, there are two aspects. I mean, one is, let's say, software performance, which in our case boiled down to minimizing stuff. So to optimize some things, we had to minimize amount of data sent between nodes. We have to minimize, let's say, a few things which I'll tell you a bit later. But other things which are really important is when we are dealing with 100 nodes cluster, which we need, you have to have some automatic nodes, automatic measures to provision, to manage the system. It is very important. Without it, you will not be able to handle such system. So you have to have automatization, you have to have provisioning of new nodes and stopping out old nodes and stuff. You have to have built-in debugging and logging tools, for example, those real-time statistics. And you have to have other tools to handle nodes in the cloud. So when we did tests, when we had 100 EC2 nodes started for the Oortle, we had to test it somehow. How to test a cluster of 100 nodes, start another 100 nodes, and do a stress test. So basically, we did it, and basically, if you want to handle such big systems, you have to have a lot of tools which will help you. Without it, you will not be able to solve it. So minimizing, optimizing the performance. First of all, you have to minimize any message flow between nodes. Network is not infinite, bandwidth is not infinite, so you have to make sure that if you're working with broadcast, you send only one message per node in best case. But the problem that messages can be lost, even in Erlang. In this case, we employed an optimistic approach, which in best case used only one message, but if something went wrong, it was able to recover from it. In such systems, you have things like real-time statistics, so you have to minimize the bandwidth which you're using by those real-time statistics by logging and other auxiliary stuff, or maintaining information about the cluster itself. Provisioning is, when you have a cluster, you should be able to scale it up and down. You should be able to start new nodes and close new nodes. So you have to have tools for it. And for automatic provisioning, we just in our case employed a pretty simple solution. Basically, we define the limits. Let's assume that one node can handle at most 50,000 connections. I'm talking about small EC2 nodes, which are pretty weak at most, but it should be handling at least, let's say, 10,000 connections. So if our average in the cluster is more than this or less than 10,000, we either start the nodes to handle more connections, or we stop other nodes and move clients from one node to another. The notion of moving clients in our system was very important from the other perspective, because in such big systems, nodes crash. It always happens, there are always some problems in the clouds. You are not given full guarantee that every node you start will be alive. It can crash, and it happens always. So your client should be able to detect it and reconnect to other nodes. This is essential, and it is essential for situations when you want to scale down your cluster, if you want to save money by not running everything all the time. Okay. One very important thing which we're talking about today. If you have such a system, you should be able to upgrade it on the go without stopping it, because there are always connections. Some users are using it, but it's very important. Aside from code upgrades, you should have to implement always rollbacks, because upgrade can always fail. You can make some stupid error, and which will bring half of your nodes. So you should be able to always roll back your changes back to previous version, which was slightly flawed but not disaster. It's very important. Reliability. There are a few aspects of reliability. Most important for us was guarantee the delivery of messages to our users. In our case, it was not really, it was not very hard limitation, because we was able to live with, for example, different reordering of the messages on different clients. It was not bad, because let's assume that we are updating comments for the post. It doesn't really matter if on one client user A comments first and user B comments second, and for other client it is vice versa. It's okay in our situation. But aside from this, we have to handle the situations, for example, updates of the blog post itself. We have to apply patches to the text of the blog post in correct order, because we just failed. So we employed the approach where we guarantee ordering of messages per sender, not per receiver. So we guarantee that if I send a message to you, then it will, from me to you, it will be delivered in the same order as sent. But if there are two persons, we don't guarantee the ordering. In such systems, it is important to find places where you can cheat a bit, because if you would have to guarantee full ordering for all the elements, all the senders in the system, you are screwed, because such protocols exist, but there is only randomized, as far as I know, of course, only randomized approaches guarantees convergibility of the ordering of such cluster, and all such solutions are using a lot of message passing between separate nodes. So if we have a large number of nodes, large number of clients, we are not able to handle it perfectly, but just not ordering everything fully is a good solution for us in our case. And if you build such big systems, you always have to look for such interesting things which you can cut corners. Because without it, if we have to implement full ordering, we would have like our one node would be able to handle probably like 10,000 connections, not 1 million connections as we do. So aside from this, messages can be lost. We have to be able to resend messages to the subscribers when the subscriber knows the last message he received. So every node has to have a cache of the messages which were routed through this node, so client can so they can be resent. But on the other hand, what about very slow clients? What do we do if some client is so slow that it asks for the message which is no longer in the cache? This problem basically has no great solution, because the only solution would be to have a full cache of every messages, which is unreal. And so we just chose a very familiar solution for this, let it crash. Basically, if the client asks for all message which we don't have in the cache, we ask him to refresh the page. It can happen, but it happens only very, very infrequently, so we can use such cheats. But this way we are limiting our memory consumption. Okay, I will skip this part. Oh, no, maybe not. The things on the previous slide which I described were implemented in the system itself as the problem arises. So we implemented reordering one day, idempotency of messages the other day, and caching the other day, because we didn't know about those problems when we were implementing it. So after we knew all the problems we had, we I have invented the, let's say, Outcast broadcasting mechanism, which is suited for our use case. It may not work for others because this works only per topic. So every guarantees which we are giving are per topic. We are ignoring, for example, ordering in 2 different topics. It is not important for us, so we skip it. We use message cache, which I talked previously, but the important thing, if we have a cache of messages and we have a new node which just started, if that node doesn't have any cache yet because he never received any messages, he never routed any messages, so every client which will connect to it will crash because he will ask for a message which that new node doesn't have. So our solution was to synchronize caches between send cache to that new node, any cache, and rely on recovery mechanisms in the this algorithm, which will fill all the missing messages in this cache, because this cache can be pretty old. So this algorithm handle reordering. It makes uses of vector blocks a lot, where we have to maintain IDs of last sent message from every node in the cluster. So we maintain so-called vector blocks, which is a really cool thing which we should read about, which allows us to handle conflicts where 2 nodes sends a message to one topic at the same time. This will be detected. This will be marked as a conflict, and when this message arrives to the destination, our client JavaScript code knows that this is a conflict, and those 2 messages are conflicting, so he will be able to, for example, try different order of patching the blog post or other things. And again, if, for example, we are the one node is too slow on filling up his local cache, it's not up to date, and it knows about it because other nodes informed it by gossiping mechanism that it has 2 old messages. We'll just crash the node. Clients will reconnect to other node, and if we're above our overloaded level, we'll just start new node. It just works. And the thing which I already mentioned, it's fault tolerance. In such systems, node can and will crash. You have to design your systems assuming it will happen. So you have to provide failovers. You have to provide possibly spare nodes in the cluster, because on any cloud, nodes doesn't start as fast as you would like. It doesn't. It takes few minutes, not few seconds. So it is a good idea to have some spare nodes running. It helps. Yeah, and since one of the most important points, if we have such cluster which has a single point of failure, you have to eliminate it. So if you have a control node in our system, you have to provide a failover to it, because if it fails and there is no other node to take over it functions, cluster will dissipate and everything will crash. And I would like to mention that the other other developers working on this project, aside from me, Joel Raymond implemented the very basics of this project. Anton Fedorov worked on a lot of automatic provisioning of the system and scaling it in the cloud. Andrei Sorokov worked on things like client code and stuff. And that's all. All right. Any questions?
When you moved away from Resultant, you said that you now use Proto.ws,
Yeah,
right?
that's just the code taken from Resultant. We stripped off all the things which we don't need, and we left only the protocol parsing code, which is implemented in a functional style. So we don't use, it's just a library which parses the code, and we just call a function which has interface similar to folder, and provides accumulation or complex and stuff. So we just parse it.
Okay. So this part, Proto.ws, is still continuing.
Yeah, we will continue it because we need it. We looked at Codeboy and other places which implement handling of WebSockets, but all of them have had too complex, let's say, as far as I remember, they used not one process per WebSocket. There was no pure functional code which was parsing the protocol. So we just took this parsing and put it in another library, which maybe will be reused by Codeboy someday.
Is it right when I guess that you didn't use OTP, GAN supervisor and so on?
No, we used it.
You used it?
Yes. I mean, the problem is that we don't. Our nodes are disjoint. The only thing which communication which happens is just broadcasts, basically broadcasts of messages and broadcasts of some additional information like status of each node. So we don't use OTP failovers, for example, between two nodes because, let's say, as far as I know, they have been implemented for situations when we have those nodes very close to each other. For good network, when there is a very short latency and stuff, but we have another situation, so we implement this ourselves. So we used OTP stuff inside the node, which is very helpful, but our communication between nodes is separately implemented.
Okay. Did you also use GAN server for the main workers?
Not for workers, because GAN server takes up too much memory.
Yeah.
Problem in such scenarios is, at least in our case, we always hit the maximum memory limit. We were not able to handle, if I recall correctly, more than 800,000 connections on one 36 gigabyte RAM hardware, because different parts of the system takes memory for handling connections, especially as far as I remember, kernel itself takes about 15 kilobytes at least of memory per connection for buffers and stuff. GNTCP takes another 30 kilobytes, and it adds up. So we were not able to handle as much things. So we avoided at least small bit, which is GAN server, which takes a little bit more than pure processing.